So what I'd like to do is ask Mike Wehner to come up. He's going to introduce our keynote speaker. Mike is Assistant General Manager at Orange County Water District, one of our member agencies. He oversees a number of programs at the district, including water quality and the technology group, the health and regulatory affairs, as well as hydrogeology. Mike serves on NWRI's board. I have a chance to work with Mike closely, and that's always been good for me. Mike?
Thanks, Jeff. I'm really pleased to have the opportunity to introduce our keynote speaker this morning. David Sedlak's professor of civil and environmental engineering at UC Berkeley, and his research is focused on the fate of chemical contaminants in the environment and on the development of sustainable water supplies. We at Orange County Water District have worked with David many times over the years. He's been at UC Berkeley for 19 years, and we've probably worked with him for most of that time, one way or another, beginning with the investigation of NDMA formation in Water Factor 21, working with Bill Mitch when he was in David's lab, studying the potential for wetlands treatment to reduce hormones in the water of the Santa Ana River, and more recently in the creation of the National Science Foundation's Engineering Research Center in conjunction with Stanford, Colorado School of Mines, and New Mexico State University. David's the Deputy Director of the Renew It Center, which is known as Reinventing the Nation's Urban Water Infrastructure. I had to write that down to make sure I get it right. Over the years, I've encountered David in many different settings, and he was a little afraid I was going to bring up his lazy years, as he put it. I encountered him on the beach at, it's Bronte Beach down near Sydney in a barbecue. David was nice enough to host a couple of us when we were down there, Rick Sakaji and me, when we were down visiting for an AWARF project. And so I got to see him in a really relaxed setting where you could see the whitewater from his study in his home, just a gorgeous location, when he was on sabbatical from UC Berkeley. I've run into him completely by accident in the hallways at Singapore PUB. I think we're both surprised to see each other there. And the thing I think I've enjoyed the most is when I've run into David and he's leading groups of students. And I see the enthusiasm that he has for learning and for knowledge and the science that he does as part of his work. And I can see how infectious it is with students. I've known a number of his students from Singapore and students from the US, and how they've caught some of that enthusiasm from David and the interest in the science. His latest accomplishment, though, is a book entitled Water 4.0, The Past, the Present, and the Future of the World's Most Vital Resource. We'll learn more about the message in that book with David's talk today, which is entitled Two Visions of the Fourth Revolution in Urban Water. Please join me in welcoming David Sedlak.
Get this on the screen. Thanks, Mike, for a great introduction. It really is an honor to be here in Orange County. Sometimes it feels like a second home, and that's kind of an interesting concept for someone whose other home is Berkeley. Some of you know what that's about. And it also is an honor to be here for the event tonight of Rhodes receiving the Clark Prize, because really I think of him as being an important part of the story I want to tell you about today. So the title of my talk is Two Visions of the Fourth Revolution in Urban Water. And the thing about revolutions is that people don't see them coming. And I think after today's conference, you'll agree with me that we're on the cusp of a revolution. And the revolution that we're seeing has a variety of different forces driving it. But the main forces, I'll tell you about them today, driving this revolution. And as you listen to the talks today, you'll see examples of the revolution. The revolution starts in places where the existing water infrastructure is no longer able to deliver the services it needs, and there's a radical change that's needed. And that change involves innovators who work with organizations that are under the stress to develop new ways of creating urban water services. And those services spread from the early innovators and the early adopters out to the whole country and the whole system. And I want to tell you about some of the revolution, the outlines of the revolution that are happening here in California, but I also want to tell you how it's not the first time urban water systems have undergone a revolution. Our urban water systems have undergone 3 other revolutions, and they followed a very similar pattern, where the existing approach for providing water, treating water, and developing the services we come to expect is no longer adequate, and a change is needed. And what happens is innovators work on the change spreads, and then we forget that there was even a revolution that happened. And so I think as we go forward, it's important to have an understanding of those revolutions that have occurred. But today I also want to tell you about 2 visions for the next revolution in urban water. The first vision is the vision that most of us in this room have bought into. It's a vision that involves centralized water supplies and centralized treatment and water service provision. But the other vision, the vision that's not well represented in this room, involves distributed treatment, distributed water supply provision, and is usually not talked about because it's not as far developed. And it's usually something that you hear architects and city planners talking about. And oftentimes the people who are proponents of the vision that involves centralized treatment are not particularly fond of this way of providing water services and are a little cynical about its potential. And I want to show you today that these 2 sometimes contradicting approaches to the next revolution in water have a role to come together and develop a hybrid system. And that hybrid system will play off of the strengths of the 2 different approaches and ultimately leave us with an urban water system that is more resilient, more efficient, and more effective. So let's start with the first revolution in urban water. I'll call it urban water 1.0, like the first version, and it happened in Rome. And now Rome wasn't the first place where water supply was needed. There were many previous civilizations where water supply was organized in some way, but Rome was a little bit unique in terms of its size, its wealth, and the way that its citizens just love water. And so at Rome, at the height of the Roman Empire, was providing the citizens of the city close to 100 gallons per capita each day. At least that's what some estimates of it are. And so that's a lot of water compared to other people in the ancient world. And so this map shows you some of the many aqueducts, a little photo of an aqueduct. It's actually not a Roman aqueduct, it's an aqueduct in France, but it gives you the idea, and we've all seen these before. But I just like 2 aqueducts stacked on top of each other. But maybe just as important as the aqueducts and water service provision was the water distribution through a network of pipes, sometimes underground pipes, sometimes made of lead, sometimes made of terracotta, and the sewers. Because Rome was built in a low spot near the Tiber River, and the cloaca was needed to drain the city of Rome. And the cloaca, the informal sewer system, which initially started as ditches, eventually got covered up and became the sewers of Rome. And so the imported water system and the sewers of Rome became the first version of urban water. And when the world started getting wealthy, about 12 or 13 centuries later, they turned to this approach of providing urban water services. And so when London and Paris started growing in the 19th century, or maybe more relevant for our discussions here today, when the United States started growing in the late 19th century and early 20th century, we turned to the same approach of imported water and sewers. And so if you think about New York City and its wonderful gravity-fed water supply with the Catskills and Croton watersheds delivering water to the city, and sewers following the Roman model discharging waste into Long Island Sound and the Atlantic Ocean, that's very similar to the Roman system, but on a much grander scale. And on an even grander scale yet is the western United States, exemplified by the Colorado River, where you have the Central Arizona Project and the Colorado River Aqueduct providing water for a lot of the people who live in the American Southwest. So there's an incredible upscaling of this first version of urban water, but it wasn't all that different from the system that the Romans developed. So water supply, sewage disposal, water supply, sewage disposal, water supply, sewage disposal. Eventually, this becomes too dense, and the sewage disposal for one community becomes the water supply for the next community downstream. And so the next version of urban water infrastructure was designed in response to the fact that people's drinking water intakes were very close to other people's sewage outfalls. So there's no sewage treatment, there's no drinking water treatment, the upstream community discharges to the river, the downstream community gets sick. And the best example of that are the towns of Lowell and Lawrence on the Merrimack River in the United States. And so in the case of Lowell and Lawrence, you had Lowell, the upstream town, discharging its sewage into the Merrimack River about 15 miles upstream of the drinking water source for Lawrence, and people getting typhoid fever. And this was a common occurrence in the United States and lots of different parts of Europe in the end of the 19th century. So this newspaper article from the New York Times, it should say 1891, just shows you that people realized that there was an epidemic. And the town of Lowell was able to find a clean water supply that wasn't contaminated by sewage. But the town of Lawrence had no such alternative available to them. So in desperation, they did what desperate people often do. They turned to academics. And the academics that they turned to were the Lawrence Experimental Station. That was MIT's experimental station that was established in Lawrence, partially because it was a great place to study this problem. And people like William Sedgwick, who was the first sanitary detective, if you will, helped figure out the source of the disease outbreak. And people like the prodigy Alan Hazen, who was one of the people who helped pioneer slow sand filtration, developed a system for treating water. And that sand filtration coupled with chlorination basically solved the typhoid fever outbreaks. And so the levels of typhoid fever returned to the background levels of communities that weren't drinking contaminated water. And people like Abel Woolman from Johns Hopkins and others helped spread this innovation all around the world. And so by the first part of the 20th century, it was commonplace to filter water and to chlorinate it. And typhoid fever and cholera and problems like it were largely under control in developed countries. So that's the second revolution in urban water. Everything proceeded well until people realized that it wasn't enough just to worry about treating the drinking water. All of this sewage that was going into rivers was causing problems. And they were causing such bad problems that cities were no longer nice places to live. So near me, near Oakland, the town of Alameda, people started moving away because the sewage from Oakland and Berkeley and the East Bay Hills was dumped out into the mudflats by the Bay Bridge. And it became so hard to live with the smell of hydrogen sulfide and sewage and the other affronts, that a solution was needed. And the solution that was developed was sewage treatment. So activated sludge treatment, maybe some of the early research, again, done by an academic, Gilbert Fowler at the University of Manchester, who was influenced by what he saw at the Lawrence Experimental Station, resulted in a good system for treating sewage, whether it was the trickling filters or the activated sludge treatment plants. They largely were able to alleviate the aesthetic problems of fish kills and hydrogen sulfide that was associated with raw sewage discharges. And so then other researchers, academics like Charles Gilman Hyde, and I wasn't able to find a picture of Professor Hyde, but this is a picture of the original civil engineering building at UC Berkeley. I think it was there when roads, no, it wasn't. I think it got knocked down long before that, but you can see it here. And there were a variety of people who helped spread this idea of sewage treatment as a way to solve urban water problems. And in the late 1960s and early 70s, a window opened. People became aware of the problems that were causing the environment. Rivers started catching on fire, and people noticed problems like DDT and its effect on top predators. And so a window of opportunity opened, and the Clean Water Act enabled the investment in sewage infrastructure. And this figure here just shows you some of the investments that were made in the United States in sewage infrastructure, to a point where this revolutionary idea of sewage treatment, which started slowly in the beginning of the 20th century, spread around the whole country and created a new way of delivering urban water services. So here we are in the 21st century, and I'm making the argument that we're due for another revolution. And I want to tell you a little bit about the reasons why I think we're heading towards another revolution. The first one is climate change. And I don't want to steal Jerry Schnorr's thunder. He'll talk to you a little bit later about climate change. But in a nutshell, the reason that climate change is an issue is that it's going to become wetter in the places that are wet, and it's going to become drier in the places that are dry. So this figure here just shows you a map from the latest IPCC report, which just shows you where the changes in precipitation patterns are going to occur. And in the western United States, the precipitation patterns that give us our winter precipitation are going to move further to the north, meaning that the southwest and southeast of the United States is likely to become drier. Australia is likely to become drier. The Mediterranean countries are likely to become drier. Other places are going to become wetter, but there's certainly going to be a water supply issue. And you can see here in this figure from last week from the drought monitor in the US, the dry conditions in the US, and maybe some of you remember the dry conditions in Texas last year. Another driver for a change, a revolution in urban water systems, it's I'd characterize as resource considerations. So this map shows you from the U.S. Global Change Research Program population changes, and the map just shows you in blue the areas where population's decreasing, and in orangey red the locations where population's increasing. And what you can see is that in the United States the population's moving to the dry places. It's moving to Florida, it's moving to Texas, it's moving to California and the Southwest. There's a new concern, new interest in reducing greenhouse gas emissions. And so a lot of the urban water systems that were developed during a time when energy was inexpensive and we weren't too worried about carbon dioxide emissions are coming under scrutiny. And so this is the famous greenhouse gas cost curve from McKinsey that mainly deals with the energy sector. But we could imagine similar cost curves for the water sector. And suddenly pumping water up in the California into Southern California or up to Tucson, Arizona, becomes low-hanging fruit in terms of lowering our greenhouse gas emissions. And if we could reduce the amount of water that we have to pump way uphill, we have ways to reduce greenhouse gas emissions. So there's a good motivation there. And finally, there's a new interest in recovering nutrients from our wastes. And so this is a picture from a very nice article that showed up in ES&T a couple of years ago. And it's a picture of someone, I guess, putting struvite in their hands. I'm not sure I'd do that from a sewage treatment plant, but that's me. But there's an interest in recovering the phosphorus and the nitrogen and the organic matter from sewage treatment plants. And this is going to become a bigger driver in the future. So here are the two visions of the urban water of the fourth revolution. This is the vision that we're familiar with. It's exemplified by William Mulholland, who really was the engineer who thought about what water supply should look like. And if we were to ask Mulholland about what the future of urban water infrastructure would be, he would say it's centralized. And he would say it's centralized because it's economical. It's a logical evolution of all of the money we've spent on our water infrastructure. So let's not abandon what we have, let's improve it. It's run by professionals, and those professionals are competent in providing oversight. Water supply and sanitation is a public service. It should remain that way. It shouldn't be farmed out to the private sector. And the ultimate objective is to be safe and reliable. And I think many of us have built our careers around that objective and take the engineer's approach. But there's this other vision of urban water infrastructure, here exemplified by the architect and planner Le Corbusier. And this school thinks a little differently. They think that the solution to urban water infrastructure issues involves distributed systems and making individual buildings or individual blocks of houses autonomous and able to treat their own sewage and provide their own water. And they would advocate for this because it provides a resiliency that you don't see in centralized systems. Instead of thinking that it's a logical evolution, they would say it's a much-needed revolution. They would look towards the grassroots support of the public, and anyone who's dealt with the public on issues like gray water or household water supply and low-impact development would realize there's more support among members of the public for this approach to water than there is for the large centralized system. They would tout the independence of the system and the fact that it gives people control of their own destiny. And they would talk about its flexibility and its ability to evolve in the future. So what I want to do is I want to spend a little time showing you primarily this centralized vision and how it's being realized here in California, giving you a few examples of the front lines of the revolution and what we could expect to spread to the rest of the country through the result of the innovative work of some of the people here in this room and others. And then I also want to talk about this other view and the ideas that have been proposed, and maybe they're not as far developed, but I want to show you what they are. And I want to end by thinking about how these two visions can come together. So here's the current system that we have. I'd call it Water 3.0, the centralized version. This is what Glenn Daiger, the president of the International Water Association, calls the take, make, waste linear approach to water supply. That is, you take imported water into the system, you put it through water treatment, Water 2.0. You use it in the city, only one flavor of water, potable water, gets used for absolutely everything, and then it becomes sewage. And that sewage goes to a wastewater treatment plant, Water 3.0, and then it gets discharged to the environment. And if the city got rain in it, then there's stormwater runoff, and maybe that runoff goes into the wastewater treatment plant, a combined sewer system, or maybe it bypasses the wastewater treatment plant and becomes a separate sewer system. When we talk about the next version of water, Water 4.0, the centralized version has a lot more arrows on it. It looks a lot more complicated. But the general idea is that water gets recycled in a loop. And so let me show you kind of some of these loops. First of all, we don't call them sewage treatment plants anymore, do we? We call them resource recovery facilities because that's what they do. They recover resources. And sometimes when they recover those resources, they return them directly back to the city as non-potable water, or sometimes they return them to the city as potable water, so-called direct potable reuse. Or maybe they discharge them to an aquifer, and we manage that aquifer, soil aquifer treatment, aquifer storage and recharge, recovery, whatever you want to call it, and we send it back to the water treatment process and it goes back into the city as the potable water supply, or maybe it gets used within the city for non-potable applications. And we also could discharge it to managed surface water. We don't just ignore the surface water, but we consider the surface water part of the infrastructure, engineered treatment wetlands, managed hyperrheic zones in rivers. And these systems become part of the treatment system and can either be used for pre-treatment before going into a managed aquifer, or maybe even like for example, in the Tarrant Regional Wetlands in Texas, into a reservoir for a drinking water treatment plant. That's the centralized version. Let's see a few examples of the centralized version. Here's an example close to home for me. It's in Oakland. So East Bay Mud, the local utility, if you've ever driven over the Bay Bridge, it's the treatment plant right in the middle of the cloverleaf there. East Bay Mud, they're not very worried about their water supply. They have an adequate water supply, but they're looking to recover energy. And they had excess capacity in their anaerobic digesters, and so they got this idea of bringing in organic waste from other industries and other applications and converting it into biogas. And so this figure here shows you the progress they've made in producing energy. So by bringing trucked waste, winery waste, slaughterhouse waste, all kinds of organic matter, household compost even they're experimenting with, by bringing that into the treatment plant, they're able to provide about 90% of the electricity they need to run the sewage treatment plant. And they have plans to bring it up to 100%. That's part of this resource recovery part. It's no longer just a sewage treatment plant, it's a resource recovery facility. Closer to where we are, by the Los Angeles airport, you might find West Basin's Edward C. Little water recycling facility. This is a really interesting water recycling plant that does something that I'd refer to as tailored water. That is, it does water recycling, but it produces 5 different flavors of recycled water. It produces irrigation water, so-called Title 22 water for landscape irrigation. It produces water after reverse osmosis that can be used for groundwater recharge, but it also produces 3 different kinds of industrial waters. It provides waters for cooling towers, it uses reverse osmosis and prepares the water to go into low pressure boilers, and it even produces a little bit more treatment and prepares the water to be used in a nearby oil refinery. And the interesting part about this water recycling facility, is that as the needs of the different customers change over time, it can change its mix. And so it's not held hostage to just landscape irrigation or just one kind of cooling water. And so if the community needs less landscaping water, that's okay. More water can go to one of the other needs. Now here, closer to where we are today, is the Santa Ana River, and here's an example of a managed aquifer. And so along the banks of the Santa Ana River are the Anaheim Lakes, right about here. And what the Orange County Water District does is they route water from the Santa Ana River, so here's the main channel of the Santa Ana River, into the lakes, and the water percolates into the aquifer, and it becomes a drinking water supply for the nearby community. And so the aquifer and the microbes associated with the sand during the infiltration process are part of the treatment process. And that Santa Ana River, right there in Anaheim, in the summertime, is essentially 100% wastewater effluent. So it's a potable water recycling project using a managed aquifer as part of the treatment. Now further up the Santa Ana River, you can find the Prado Wetlands. And the Prado Wetlands are an example of a managed surface water. This is a facility that was developed behind a dam. So a dam was put on the Santa Ana River to protect the lower part of the watershed from flooding, and it became very popular with duck hunters and everything was fine. But then at some point, Orange County Water District realized that they were running into problems with high levels of nitrate in the Santa Ana River, because after all, it was the sewage discharge from Riverside and San Bernardino and the Inland Empire communities. And so working with my colleague at UC Berkeley, Alex Horn, they designed a series of vegetated wetlands, and those wetlands did an excellent job removing nitrate. So part of the managed surface water improved the water quality by removing the nitrate through denitrification and making the water safe to drink. Now, we've been working, as Mike mentioned a little while ago, with Orange County Water District, thinking about removal of trace organic contaminants in wetland systems. And one of the ideas we came up with was something we called an open water unit process wetland cell. And this is a picture of the pilot scale facility that we built at Discovery Bay, and a reference to a paper that came out in Environmental Science and Technology a few weeks ago. But we found that if you don't let rooted plants grow and you leave the water at about 30 centimeters depth, photochemical reactions and a unique type of microbial community that develops at the bottom of that sunlit water column do an excellent job at removing trace organic contaminants. We were seeing removal of pharmaceuticals and personal care products that were an order of magnitude better than what we were seeing in the vegetated wetlands. And this open water cell was also able to remove nitrate. And so, due to our long-term relationship with Orange County Water District and their interest in improving water quality through managed surface waters, they took our idea and upscaled it. And this is a picture of the open water cells that were built on the Santa Ana River at the Prado Wetlands. And for scale, I've circled here, I guess that's a front-end loader and a tractor. So you get an idea of the size of this thing. And I heard just yesterday that this is going to be filled with water on Monday and used as a way for removing trace organics in the Prado wetland system. Okay, let me turn to think about this decentralized version of urban water systems. When you hear about this decentralized version, you might see something like this. This is the kind of idea that Peter Wilderer pushed, or that Rolf Otterpohl in Germany talks about. You can take a house and make that house an off-the-grid house. And that house can do all kinds of wonderful things for you. For example, you could replace the normal toilet with a vacuum toilet, put the food waste from the house into an anaerobic digester, and in a miniature version of what happens at the East Bay Mud Treatment Plant, make your own biogas. Let me see if I go backwards here. Somehow that got pushed. Help me. Somehow it went forward. Sorry, I'll just go with it here. You can make your own biogas. And that biogas can be used to heat water. And then you could capture the roof water and use that roof water as a drinking water supply. And you can have a separate gray water stream and use that gray water stream for landscape irrigation. So that's one version of a decentralized water infrastructure where you take a house and you take it off the grid and you make it work for you. And those systems are still quite expensive. And people talk about how they may not be practical because maybe you can't get rid of all the water in the wintertime, or you have to put a lot of effort into managing them. But they're one approach for taking a house and taking it off of the urban water system and having a different vision of the fourth generation of urban water. Maybe that's a little far-fetched now. Maybe the technology's not there to build those kinds of houses. Here's something a little bit more practical and down to earth. This is a membrane bioreactor. So in the center of this figure, you can see, oh, golly. Sorry. There we go. There, I could have gone back to that one. I'm not going to touch this anymore. I'll just point. In the center of the figure, you can see a membrane bioreactor. This is a membrane bioreactor that's being operated at Colorado School of Mines by our colleagues Zahi Kath and his students for a while now. And that membrane bioreactor treats the wastewater from a student dormitory. And that kind of technology could be used to provide irrigation water. It could be used to flush toilets within buildings. It could be used for groundwater recharge, and maybe someday it could even be used for potable water reuse. We could treat that water the same way we treat water in the space station and make sewage suitable for human consumption. And so what you have there is a vision of breaking the house off the grid and doing all the kinds of things that we do in the large centralized system and doing it in a smaller footprint. And that has some real advantages because you don't have to pump the water around the city all kinds of crazy distances. You could reuse it right where it's produced. The other kind of distributed water infrastructure that we hear a lot about is green roofs, or green streets, or low-impact development. Whatever you want to call it, it's got a lot of applications and a lot of proponents. And so in the eastern United States and the upper Midwest and the Pacific Northwest, where there are a lot of combined sewer systems, instead of building sewage bypass tunnels, people have been investing in bioswales, green roofs, cisterns that collect water. And so instead of taking a centralized approach to solving the problems of combined sewer overflows, this distributed approach can be used. And sometimes it's more expensive and sometimes it's less expensive. But in all cases, it has a lot more public support than digging big concrete tunnels throughout the city. So we've got these two visions. We've got the centralized vision, which is the one that we all kind of are part of and have put a lot of our energy into. And you have this distributed vision, which either posits taking houses off the grid or just reusing water close to where it's produced, or solving the urban drainage system problems by going to these delocalized solutions. So why don't they agree together? Well, maybe the problem here is that we've been looking for our solutions in the wrong places. Think for a moment with me about the different niches where this decentralized approach might be more practical. Think about a rural community. Rural communities are off-the-grid houses. They use a 19th century technology of a septic tank and a drain field. They use local groundwater as a drinking water supply, and they handle their stormwater with drainage ditches. And so if we can run a water supply for a rural community on 19th century technology, imagine what we can do with 21st century technology. I think we can make these systems function at a lot higher density than what they currently work at. So think about the suburban communities on the edge of the city. With a modernized version of distributed water treatment, they could become practical. Why do people upgrade from this distributed form of water treatment to a centralized one? Well, they can no longer acquire enough water and dispose of the sewage that they have. And so you think if we can reduce the consumptive water use in the house by 70%, by eliminating outdoor landscape irrigation with potable water and doing the best we can with reducing potable water consumption through conservation, suddenly the water demand's a lot different. And you could provide water through a combination of shallow groundwater and roof water collection. And suddenly you're generating a lot less wastewater that needs disposal. And suddenly these solutions look good in not just in rural communities, but in suburban communities. And after all, when you look at a city and the way it's laid out, not every place is densely populated like downtown San Francisco or Manhattan or downtown Chicago. Most places look like Orange County, where there's a lot of open space between the houses. So a path forward. I think that the time has come for us to start getting a little bit more serious about this second vision of urban water infrastructure. And I think the people who push the second vision of urban water infrastructure need to start talking to the people who've put a lot of thought into centralized water infrastructure. And so I see them working together. In the centralized core of our most densely populated cities, I think there's a role for this fourth generation of centralized urban water infrastructure. We see it playing out here in Southern California, and we see the benefits it offers us. But this other vision of urban water infrastructure, the little red circles here with the different approaches, that has a place too. It's obvious to me that one place for it is on the edge of our cities as they develop out, as we think about greenfields developments and redevelopment on the edge of cities. But there are other places we haven't even thought of yet. And there are other benefits that they might give a city. For example, think about it this way. If someone built an off-the-grid housing development in a city that had a combined sewer system, that's that much less water that goes into the already overburdened pipes of the city. And so why would you ever let anyone build a new community in a place that has a combined sewer system and allow them to hook up to the centralized infrastructure? It's got to be less expensive to find a way for them not to put an additional burden on that wastewater collection system. So these kinds of thoughts, I think, will become more important in the future to us as we think about the potential to build out hybrid systems of centralized and decentralized water. So some final thoughts. I think the time has come to start preparing seriously for the fourth revolution, because there are a lot of drivers that are going to take us there. And you think about climate change, even if we solve our problems with greenhouse gases tomorrow, we bought into a certain amount of climate change, and we're going to see changes in our water supply availability. We're going to see changes in population. We're going to see a continuing pattern of underinvestment in urban infrastructure. So there's a reason to prepare for the fourth revolution, because it's coming. I think there are things we can do. Priming the pump is one of them. If you look at the previous revolutions, it was a crisis which created the need for a revolution, and the technology had to be there. And those technologies that often end up being the practical ones at the end of the day, they're not cheap at the beginning. They need time for experimentation. They need time to become less expensive. Think about seawater desalination 30 years ago. It was impractical. It was way too expensive. Now, it's probably a better option than pumping more water over mountain ranges, and people are starting to build desalination plants around the world. So a 20 or 30-year time for development is needed, and we have to prime the pump, and we're not doing enough pump priming. We also have to think differently about the way we do city planning. I think we have to think about what I would call no regrets planning. If you see the future of urban water being a stronger wastewater stream as water conservation comes to bite, more water recycling and resource recovery, hybrid systems of centralized and decentralized systems, you have to start planning differently. You have to think about the way you invest in infrastructure, because those investments have lifetimes of 50 or 100 years. We also have to be ready for windows of opportunity. When you study the way in which revolutions happen in urban water infrastructure, they don't happen immediately. They don't happen slowly. They happen through some event that focuses the public attention. And that's called opening up a window of opportunity. And when those windows of opportunities open, we have to be ready with solutions. I think we missed a window of opportunity during the stimulus package a few years ago, because everything had to be shovel-ready, and the fourth generation of urban water infrastructure wasn't shovel-ready. So the importance of research, I guess that's my last thought here. I think that there are some areas where we'd be well served to invest some additional research effort. One is thinking about decentralized treatment systems, this fourth generation of urban water infrastructure. It's still not clear to me exactly what it's going to look like, and I think we have to think about how to enhance the performance of those systems and understand the uncertainties associated, especially with those natural treatment systems, which engineers aren't quite comfortable with yet. We have to think about how to enable these decentralized systems. The decentralized systems are going to have a role to play, and I would argue that they need a lot more attention from engineers and not just architects. I have an architect friend. He always tells me, well, we'll just put a living machine in the building and that'll be fine. And I say to him, well, there are other options that you might want to consider when you try to find a way to do decentralized on-site treatment. And then I think there's also a role for us in trying to understand these hybrid systems. I gave you a very vague impression about how the hybrid system might look because I don't understand it yet. And I think we all have to sit together and think about the potential costs and benefits of a hybrid system of centralized and decentralized water infrastructure. So with that, I'd like to acknowledge some of the people who've really shaped my thinking about this topic of the two visions of urban water infrastructure. My colleagues at UC Berkeley, especially Bill Eisenstein and Louise Mozingo in the College of Environmental Design. At Stanford, Craig Criddle and Dick Luthi have really had an influence on me. And of course, Jörg Dreves, who was at Colorado School of Mines and is now at Technical University of Munich. And also a couple of social scientists at AVOG in Switzerland, Christian Binz and Bernhard Truffer. Again, Mike mentioned that a lot of the research here was conducted through Renew It, and there's the web address of Renew It, and really this was a collaborative effort of a lot of people. There are about 80 of us working on Renew It. And I also want to acknowledge some of the water utilities, including Orange County Water District, Singapore PUB, and Discovery Bay. And finally, a shameless plug for the book. You can see it has its own website if you're curious about learning more. And thank you for your attention.
We have some time for questions for David. David, fantastic presentation. Any questions for David? Harvey.
A brief comment, David. I appreciate the thought that has gone into this, and I wanted to give you a little experience I had, because I think we're going to have to bring in the local health departments here in the priming of the pump. I built a home in Fort Bragg, California 2 or 3 years ago, and I proposed the use of gray water to irrigate the shrubbery around the house. I went to the local health department, and they would only approve it if they put a provision on the title, and I would have had to have paid for annual inspection fees. And I was afraid it would hurt the resale. I declined their offer, and I went with a conventional septic tank.
I think that's true, Harvey, and you see that. I think it's just in the last year or two, last year, that the gray water regulations in California were updated. So I think there's attention going into that, but it's definitely a work in progress, and we could do more with the regulation side to enable distributed treatment. Mike, did you still have a question?
Yeah, please wait for the
Joan,
microphone.
I guess Joan had her hand up over there with the mic.
I'm closest to the mic, so I'll grab it. So I wanted to know, David, thanks so much for this. Have you been giving this presentation to the public, and when are we going to see you on Jon Stewart or Colbert?
You and my daughter both want to see me on Jon Stewart. Well, the motivation behind writing a book was my discussions with newspaper reporters and presentations to the general public, not to audiences like this. And I found that people were incredibly curious to learn more about this and were not particularly well informed. And for example, when the groundwater replenishment facility at Orange County opened up, there was a short 700-word article in the New York Times, and the next day it was the most emailed story. And then you'd find follow-up articles, longer articles showing up in the popular press written by journalists, and I would be there at the breakfast table on Sunday morning muttering under my breath that they got it wrong. And so I realized that you can only complain for so long, and at some point you have to contribute to the dialogue. So all of us as scientists and engineers have that need to contribute to the dialogue, whether it's like Orange County giving presentations to civic groups and members of the public, or academics getting outside of their comfort zone and talking to people other than the students studying what they do. That's part of the way in which we build public support for the changes that are on the way.
Yes, Danny. Okay, just wait for the microphone, please. Thanks.
Denny Parker. So it won't just be the county authorities, it'll be the central regulatory authorities that'll have concerns because, well, they probably don't think of the many small plants over which they have domain as decentralized. They will view decentralized as small plants. And by far the statistics show that horrible track record for small plants in terms of performance compared to centralized plants. And there's a long history for why that is, including poor engineering by developer engineers in creation of semi-utilities, private utilities to operate these things, with not giving people the right tools, the right technology, and without centralized management that is now you start seeing more forward-looking utilities taking on centralized management, but requiring better technology. So there's a real institutional and a technology gap here. And I look at a living machine, and I wouldn't want to try to run one of those. I wouldn't give that to my neighbor to run, for instance. That's the problem. You always see individual systems. You give them to real people that have to run them. So there's quite a conundrum beyond research there that has to pick up on the management side of these systems to convince people that this can be done.
I agree, Danny. I think that's an excellent point, and I think that there are two ways to go. One is create better institutions, whether they're through public-private partnerships or allowing some of the larger utilities with the institutional knowledge to stick their nose in other people's business. The other approach is to make these things so foolproof that someone with no training can operate them. And I have a gas furnace in my house, and it has the potential to kill me and set my house on fire, but I'm not too worried, and I never pay any attention to it. And so that's the other end of the spectrum, is to create systems that are so trouble-free and so reliable that a local utility that doesn't have a great deal of institutional competence can do it. The other approach is to really up the game of the people who do it, and maybe that's by changing the institutional structure.
I think we can take one more question. Lynn?
Sure. David, hi. I'm Lynn Grijalva with Hazen and Sawyer. As I'm listening to how a decentralized system takes a lot of the stress off of water supplies, I'm sure you've given thought to how then local groundwater can be a lot more practical and supply a lot more of the water than it might have if we didn't have so much recycling. Your thoughts on that?
I think that local groundwater is an under-recognized resource, and part of the problem is that every place is different and the hydrogeology is different, and so it's hard to make a blanket statement about it. But I can talk about experiences things that I've seen happening, for example, in developing countries, where people take borehole water and apply advanced treatment and turn water that you certainly wouldn't drink into drinkable water. So suddenly that shallow water from the water table, which you would never hook a household well up to, could become potable water. And so the dynamic changes. You don't have to have confined aquifers. You don't have to have deep water supply. Maybe that's for non-potable water reuse, but there are different permutations that I think could build up in this decentralized model.
David, thank you very much.